Hello, my name is Alex Boveda, and I am an engineering student at the University of Arizona. This summer, I worked with PACT under the close mentorship of Dr. Sikang Shao and the guidance of Dr. Haridi on the application of deep learning in cybersecurity. My project is a novel network intrusion detection system, an NIDS. The purpose of an NIDS is to observe network traffic and determine whether the network is being attacked, as well as what attack is being performed. This is necessary as improvements in automated and scripted cyber attacks has increased, and the need for real-time defense only increases with it. In order to determine the efficacy of our model, we used the publicly available dataset UNSW NB15 for training as well as validation. Since there is a low significance between the normal and fact traffic of UNSW NB15, it is more representative of modern complex attacks. Similarly, our model must be able to recognize these complex attacks, which means that a simple model, such as a logistic regression model, would be insufficient for the problem. Therefore, we developed a machine learning model for both attack detection and attack classification. Here is our overall architecture. For this project, we used a data analysis approach to constructing our model. Developing our model involved preprocessing to ensure our model was fed appropriate data types for the features, a feature selection and extraction phase to increase the efficiency and reliability of our model, and model tuning to ensure that our architecture was optimized to handle the network traffic data. Overall, our model architecture first begins with a convolutional layer, which leads to two bidirectional long short-term memory layers, connected to a gated recurring unit layer, whose output is finally processed by two fully connected neural layers. Our model architecture uses a convolutional layer to identify spatial features. Although network traffic does not contain any intrinsic spatial features, by grouping together features of similar origin or behavior, the model can identify higher-level feature correlations. One of the intrinsic properties of network traffic is time dependencies. These intuits are assumed temporal features, much like patterns. To adequately identify and process these temporal features, we use two bidirectional long short-term memory (BiLSTM) layers. We use BiLSTM layers to preserve both the short-term and long-term information in a more robust manner, as well as using a single gated recurrent unit (GRU) layer, as pairing LSTM and GRU layers together has shown to increase the effectiveness of our model. Finally, we use two fully connected neural layers to predict 10 classes, 9 attack classes, and the normal class. We achieved a 90.96% multiple class accuracy score, 99.86% detection rate, and 19.67% false positive rate for UNSW NB15 using model tuning, which is highly competitive with state-of-the-art NIDS models. Although we weren't able to extract the true confusion matrix of the model, here is a confusion matrix of the untuned architecture. Here we see that the model drops several classes and creates a non-specific attack class implicitly, meaning that oversampling and model tuning is required. I would like to thank the PACT program for this opportunity, as this program has allowed me, as a student, to experience and work towards bleeding-edge research. Over the summer, I have been able to do research, perform in-depth data analysis, explore machine learning concepts, develop many machine learning models in Python, and tune both my feature engineering process as well as models. I am grateful for the aid, advice, and direction Dr. Shao and Dr. Hariri have provided for me in my research, as well as Arminda Estrada for helping me throughout the summer in providing resources and coordinating the program. We would like to acknowledge and thank the Department of Energy and the National Nuclear Security Administration for enabling this research. Thank you.